There's a comet passing through our solar system right now that is behaving how no comet should. The European Space Agency aimed their most powerful X-ray telescope at 3I/Atlas, expecting to photograph the familiar chaos of ice and gas being torn apart by solar wind. What they captured instead was something that shouldn't exist. A perfect red sphere. No tail streaming behind it. No bow shock where matter collides with radiation. No extended halo of excited atoms doing what comet atoms have done for 4 billion years. Just smooth, concentrated light emanating from an object that refuses to follow the rules. Scientists are staring at their screens, cross-checking their instruments, because if this isn't behaving like a comet, then what are we actually looking at? Stay with me, because the answer gets stranger the deeper we go. Stay with us, because the story of 3I Atlas is still being written in real time. Even as you watch this, telescopes are measuring whether that impossible X-ray sphere changes shape, whether tails finally emerge, whether the physics we know will reassert itself or fail completely. Hit subscribe to track this unfolding enigma alongside us, because what we discover in the coming weeks could force us to redefine what an interstellar comet actually is. Now, let's settle in and dive into this mystery. The European Space Agency's XMM Newton telescope just released an image that has astronomers quietly rewriting their textbooks. They pointed their X-ray cameras at 3I Atlas, an interstellar visitor currently passing through our cosmic neighborhood, expecting to see what comets always show us in X-ray wavelengths. They expected a tail. They expected a bow shock, where solar wind crashes against outgassing material. They expected the elongated, glowing signature of charge exchange reactions, spreading across hundreds of thousands of kilometers of space. What they got instead was a compact red sphere. No tail, no bow shock, no extended halo of excited atoms. Just a tight, almost perfectly round glow emanating from what should be a wildly active chunk of ice and rock, screaming toward the sun at 40 kilometers per second. The image looks less like a comet and more like a planetary nebula, or a distant galaxy, or frankly anything except what 300 years of cometary science told us to expect. You need to understand why this matters. X-ray emission from comets isn't some exotic, rare phenomenon. We've observed it dozens of times. When a comet approaches the sun, solar wind carries charged ions outward at 1,000,000 kilometers per hour. These ions collide with neutral atoms in the comet's coma, the cloud of gas and dust surrounding the nucleus. During these collisions, electrons jump between atoms in a process called charge exchange, releasing photons in the X-ray spectrum. The result is a glowing, extended structure that traces the interaction between the comet and the solar environment. Every comet we've studied in X-rays follows this pattern. Comet Hyakutake in 1996 showed a massive X-ray halo. Comet Linear in 2000 had an elongated crescent shape. Even Comet Ison in 2013, which disintegrated near the sun, displayed the classic extended X-ray morphology before its death. The physics is well understood. The predictions are reliable. 3I Atlas is breaking those predictions. The image shows a concentrated source barely larger than the nucleus itself. There's no diffuse envelope. There's no asymmetric tail pointing away from the sun. The X-ray emission appears almost spherically symmetric, as if the solar wind isn't interacting with this object the way it should. Or as if the coma structure is so unlike normal comets that our entire framework for understanding these interactions has a massive blind spot. Think about what comets actually are for a moment. These are the leftover construction materials from the solar system's formation. Dirty snowballs packed with frozen water, carbon dioxide, methane, and ammonia. When they approach the sun, heat vaporizes these ices, creating vast clouds of gas that can stretch for millions of kilometers. Dust particles embedded in the ice break free, forming the bright dust tail we see with our eyes. The gas tail, pushed by solar wind and magnetic fields, streams behind the comet in the opposite direction from the Sun. This is Astronomy 101. This is what comets do. 3I Atlas came from somewhere else entirely. It originated outside our solar system, spending billions of years drifting through interstellar space before gravity pulled it into our neighborhood. This makes it only the third confirmed interstellar object ever detected entering our cosmic backyard. The first was one I/Oumuamua in 2017, that bizarre cigar-shaped visitor that sparked endless debate about natural versus artificial origins. The second was 2I/Borisov in 2019, which looked and acted exactly like a regular comet, complete with a proper tail and normal outgassing behavior. 2I/Borisov gave us comfort. It suggested that interstellar space doesn't fundamentally transform these objects, that comets from other star systems follow the same physics as our own. 3I Atlas is destroying that comfort. The compact X-ray signature could mean several things, none of them entirely satisfying. Perhaps the coma density is extremely low, providing too few atoms for charge exchange to create extended structures. Perhaps the viewing geometry is hiding features that exist, but point directly toward or away from Earth. Perhaps the composition is so unusual that standard X-ray generation mechanisms simply don't apply. Or perhaps we're watching something that our models cannot explain. Scientists hate that last possibility. They'll exhaust every conventional explanation first, testing and retesting their assumptions, calibrating their instruments, checking for systematic errors. This is how science works, how it must work, and it's the right approach. But sitting beneath that methodical process is an uncomfortable question that nobody wants to ask too loudly. What if this object is showing us a category of interstellar body we've never encountered before? The image itself is beautiful in a clinical, unsettling way. False color processing turns the X-ray photons into shades of red, creating something that looks almost biological, like we're examining a microscope slide of some cosmic cell rather than a kilometer-sized chunk of material from beyond our solar system. The smoothness of the emission is perhaps the most disturbing feature. Comets are messy, chaotic things. Their nuclei rotate irregularly. Jets erupt from specific locations on their surfaces. Their comas shift and pulse as solar heating varies. 3I Atlas, at least in X-rays, shows none of that complexity. It glows with an evenness that suggests either incredible uniformity or a process we don't understand governing its interaction with space. The scientists who operate XMM Newton didn't expect this. The researchers who requested the observation time anticipated adding another data point to comet X-ray studies, perhaps refining models of charge exchange efficiency, or testing predictions about interstellar composition. Instead, they're sitting in conference rooms trying to explain why their target decided to ignore 3 decades of established cometary X-ray physics. You have to appreciate the rarity of the moment. 3I Atlas won't be back. Its trajectory will carry it out of our solar system forever, accelerating as it falls toward and then past the Sun before shooting back into the interstellar void. This flyby represents our only chance to study this particular visitor with our current generation of instruments. Every observation matters. Every wavelength matters. And X-ray observations, which require space telescopes and careful planning, are especially precious. So when those observations reveal something fundamentally unexpected, when they show us an object that looks nothing like what it should, we're left with a choice. We can dismiss the anomaly as instrumental error or observational bias, retreating to the safety of our models. Or we can lean into the discomfort, accepting that the universe just handed us a puzzle that might not have an easy answer. The X-ray weirdness would be easier to dismiss if it were the only strange thing about 3I Atlas. Unfortunately, the picture gets more complicated the more wavelengths you examine. Point the Hubble Space Telescope at this object, and you see something completely different. Hubble's cameras, operating in optical and ultraviolet wavelengths, reveal a classic comet. There's a coma, a diffuse cloud of dust and gas surrounding the nucleus. There's a faint dust tail extending away from the solar direction, exactly where physics predicts it should be. The images show dust plumes, suggesting active regions on the nucleus where sublimation is occurring most intensely. In visible light, 3I Atlas looks like it stepped out of a textbook chapter on cometary structure. NASA's Mars orbiters caught it too. MAVEN, designed to study the Martian atmosphere, turned its instruments toward the passing visitor and detected hydrogen emissions characteristic of water sublimation. HiRISE, the high-resolution camera on the Mars Reconnaissance Orbiter, imaged the coma and confirmed the presence of both gas and dust halos. These observations align perfectly with standard comet behavior. Water ice on the surface absorbs solar energy, transitions directly from solid to vapor, and streams away from the nucleus, creating the observed hydrogen signature. The European Space Agency's JUICE spacecraft, currently en route to Jupiter, used its navigation cameras to snap pictures of 3I Atlas in early November 2025. Those images revealed twin tails, one composed of dust particles reflecting sunlight, the other a plasma tail formed by ionized gases following magnetic field lines. Again, this is exactly what comets are supposed to look like. The dual tail structure is so common that it's become iconic in astronomy education. Amateur astronomers around the world have been tracking 3I Atlas with backyard telescopes since its discovery. Their observations report changing coma sizes, variations in tail brightness, and morphological shifts that depend on viewing geometry and the object's distance from the sun. Professional observatories confirm these changes. The comet brightens as it approaches perihelion, the closest point to the sun in its orbit. The coma expands, the tails grow longer, everything behaves normally, except in X-rays. This creates a profound puzzle. How can an object simultaneously look like a comet and not look like a comet? The answer depends on what you mean by look. Different wavelengths probe different physical processes. Optical observations show us reflected sunlight and thermal emission. Ultraviolet reveals specific atomic and molecular transitions. Infrared detects warm dust and molecular vibrations. X-rays expose charge exchange and high-energy interactions. Each wavelength is a different window into the same object. 3I Atlas apparently changes its identity depending on which window you use. Late infrared spectroscopy from ground-based observatories added another layer to the mystery. The data showed an unusually high ratio of carbon dioxide to other volatiles in the coma. Most solar system comets are dominated by water ice, with carbon dioxide, methane, and other compounds playing supporting roles. 3I Atlas flips this script. Carbon dioxide appears to be the primary volatile, with water present but subdominant. This compositional difference matters because carbon dioxide sublimates at lower temperatures than water. It can drive activity farther from the sun, creating extended periods of outgassing that might produce comas and tails even when water ice remains frozen. The carbon dioxide dominance might explain some of the optical observations. It might explain why the coma appears so active despite the object's relatively small size. But it doesn't explain the X-ray compactness. If anything, a carbon dioxide-rich coma should produce even more charge exchange reactions, creating a larger X-ray halo, not a smaller one. Geometry offers a partial escape from the paradox. Comet tails always point away from the sun due to solar radiation pressure and solar wind. If Earth happens to lie nearly along the tail axis, we might be looking down the barrel of the tail, seeing it foreshortened into apparent compactness. This viewing angle effect can make extended structures appear point-like. It's a known observational bias. But X-ray observations don't just see tails. They see the entire interaction region where solar wind meets the coma. Even viewing down the tail axis, you should observe asymmetry, bow shocks, and extended emission. The XMM Newton image shows none of these features. The compactness is too extreme, too symmetric to blame entirely on geometry. Polarimetry studies complicate matters further. When light reflects off dust particles in a comet's coma, it becomes partially polarized. The degree and orientation of polarization reveal information about the size, shape, and composition of those particles. Observations of 3I Atlas showed more negative polarization than typical comets or asteroids, suggesting unusual surface properties or dust characteristics. The grains might be larger, fluffier, or compositionally distinct from solar system materials. NuSTAR, NASA's Nuclear Spectroscopic Telescope Array, looked for hard X-ray emission from 3I Atlas and found nothing. This null result is actually important. Hard X-rays would indicate high-energy processes like particle acceleration or radioactive decay. Their absence confirms that whatever is producing the soft X-ray glow observed by XMM Newton, it's not exotic physics. The emission is consistent with standard charge exchange, just distributed in a non-standard way. So we have an object that acts like a comet in visible light, ultraviolet and infrared. It shows normal dust tails, gas emissions, and molecular signatures. But in X-rays, it presents as a compact sphere with none of the extended features that those same gas emissions should produce. The data doesn't contradict itself exactly, but it refuses to form a coherent picture. Scientists working on 3I Atlas are being careful not to overinterpret. They're aware that observational biases can create apparent anomalies. They know that instrument sensitivities vary, that signal-to-noise ratios affect what features become visible, that timing matters because comets change rapidly. The conservative interpretation is that 3I Atlas is simply a comet with unusual composition and possibly unlucky, viewing geometry. But conservative interpretations have a way of crumbling when you keep staring at them. The astronomical community doesn't panic easily. These are people who spend careers studying objects billions of light years away, extracting meaning from photons that have been traveling since before Earth formed. They're comfortable with uncertainty, trained to separate signal from noise, and deeply suspicious of sensational claims. So when the XMM Newton results started circulating, the immediate reaction wasn't alarm. It was curiosity laced with skepticism. Several astronomers specializing in cometary X-ray emissions quickly pointed out that low coma density could explain the compact appearance. If 3I Atlas has an unusually thin coma, there simply wouldn't be enough neutral atoms to generate extended X-ray structures. The charge exchange process requires collisions between solar wind ions and cometary gas. Fewer gas atoms means fewer collisions, means weaker emission, means only the densest regions near the nucleus produce detectable X-rays. This explanation has merit. The carbon dioxide-dominated composition might create a coma with different density profiles than water-rich comets. Carbon dioxide molecules behave differently than water molecules. They expand at different velocities. They interact with radiation differently. Perhaps 3I Atlas's coma is simply too tenuous in the regions where we'd normally see extended X-ray emission. Others suggested that viewing geometry remains the most likely culprit. Comets are three-dimensional objects, but we observe them as two-dimensional projections on the sky. If the coma structure happens to be oriented such that extended features point directly toward or away from Earth, they could appear compressed into apparent compactness. Add in the finite resolution of X-ray telescopes, and features might blur together into a seemingly spherical distribution. These are reasonable, scientifically sound hypotheses. They don't require new physics. They don't invoke exotic explanations. They work within the framework of established cometary science and acknowledge the limitations of observation. But they don't feel entirely satisfying. The problem is that we've observed plenty of comets with low activity levels and unfavorable geometries. We've seen comets at large solar distances where sublimation is minimal. We've caught comets at viewing angles where tails are foreshortened. In those cases, the X-ray emission becomes fainter, harder to detect, sometimes falling below instrument sensitivity. It doesn't typically become more compact and symmetric. It fades while maintaining its characteristic morphology. 3I Atlas isn't just faint in X-rays, it's structurally different. Several researchers emphasize the importance of multi-wavelength synergy, the practice of combining observations across the electromagnetic spectrum to build complete pictures of astronomical objects. Each wavelength reveals different physics. Optical shows reflected light and thermal emission. Ultraviolet probes atomic transitions. Infrared detects molecular vibrations and warm dust. X-rays expose high-energy processes. Only by synthesizing all these views can we understand what we're actually looking at. This philosophy is correct and important. It's also slightly evasive. Yes, we need multi-wavelength data to understand 3I Atlas. But the multi-wavelength data we have doesn't synthesize into a coherent picture. It synthesizes into a contradiction. The puzzle list keeps growing. Why is the X-ray emission zone so compact? How dense is the coma immediately around the nucleus? And how does that density fall off with distance? Are jets or tail structures present but simply too faint to detect in X-rays? Or are they genuinely absent? Does the carbon dioxide dominance fundamentally alter how solar wind interacts with the coma in ways we haven't anticipated? Some scientists have noted that X-ray emission depends critically on the availability of specific atoms and ions in the coma. Charge exchange preferentially involves certain species. If 3I Atlas's coma is compositionally weird, containing unusual ratios of carbon, oxygen, nitrogen, and other elements, the efficiency of X-ray generation might be suppressed or enhanced in unexpected ways. The chemical inventory of the coma becomes crucial. There's also the matter of timing and proximity. 3I Atlas is making an unusually close pass by both the Sun and Earth. At its closest approach, it came within about 0.2 astronomical units of Earth, roughly 75 times the Moon's distance. This proximity provides unprecedented observational opportunities for an interstellar object. We're seeing details that would be impossible to resolve for more distant visitors. But proximity also means rapid changes. The comet's environment shifts dramatically over days or even hours as solar wind conditions fluctuate, as the comet's distance from the Sun changes, as rotation brings different regions of the nucleus into sunlight. Observations taken at different times might capture genuinely different physical states, making direct comparisons tricky. The scientific method demands that we generate hypotheses and test them against data. Extraordinary claims require extraordinary evidence. The claim that 3I Atlas represents something fundamentally new, something beyond our current understanding of comets, is extraordinary. The evidence, while intriguing, isn't yet extraordinary enough to compel that conclusion, at least not officially. Unofficially, in conference hallways and email threads, astronomers are admitting that 3I Atlas makes them uncomfortable. The object sits at the intersection of familiar and strange. It does comet things. It also does not comet things. The contradiction nags at people who have devoted their careers to understanding these objects. What if our models are incomplete? What if interstellar space imprints properties on comets that we've never had the opportunity to observe before? What if the solar system's comets, the ones we've studied for centuries, represent only one narrow category of a much wider spectrum of possibilities? These questions don't have answers yet. They hover in the background of every discussion about 3I Atlas, unspoken but present, waiting for more data or a breakthrough insight that makes everything click into place. The clock is ticking. 3I Atlas will reach perihelion and then begin its outbound journey, fading from view as it accelerates back toward interstellar space. Every observation matters. Every wavelength matters. and the nagging sense that we're missing something important, that the universe just handed us a clue to something bigger, and we're not quite smart enough to decode it. That sense won't go away. The James Webb Space Telescope doesn't miss much. When its infrared instruments examined 3I Atlas, they found exactly what everyone feared and nobody wanted to admit. This object's chemistry is profoundly wrong for a solar system comet. Webb's spectroscopy revealed a coma dominated by carbon dioxide at levels that make water-rich solar system comets look like a completely different species. The ratio is inverted from what we're used to seeing. In normal comets, water ice comprises 70 to 80% of volatile materials, with carbon dioxide, methane, ammonia, and other compounds filling supporting roles. 3I Atlas flips this relationship upside down. Carbon dioxide dominates. Water exists, but plays second fiddle. This matters more than you might think. Carbon dioxide sublimation begins at much lower temperatures than water ice. Around 150 Kelvin, carbon dioxide transitions directly from solid to gas, while water ice remains frozen until temperatures reach about 200 Kelvin. This temperature difference means carbon dioxide can drive cometary activity far from the sun, maintaining outgassing and coma formation in regions where water-dominated comets would remain dormant. The dominance of carbon dioxide also affects how the coma behaves. Carbon dioxide molecules move faster than water molecules at the same temperature due to their lower molecular weight. This creates expansion velocities that differ from water-rich comets. The coma structure, the density profile, the way dust couples to gas, all of these factors shift when carbon dioxide takes the lead. But here's the thing that keeps scientists awake at night. Carbon dioxide should make X-ray emission more prominent, not less. Carbon and oxygen atoms are excellent targets for charge exchange reactions with solar wind ions. A carbon dioxide-rich coma should light up in X-rays like a beacon. Instead, 3I Atlas gives us that compact, nearly spherical glow that violates expectations, unless the density is the key. What if the carbon dioxide coma is so diffuse, so spread out, that even though the total gas production is substantial, the density at any given location remains too low for efficient X-ray generation except very close to the nucleus? The faster expansion velocities would distribute the same amount of gas across a larger volume, potentially explaining both the optical presence and X-ray compactness. Ultraviolet observations complicate this picture. Multiple instruments detected water signatures in the ultraviolet spectrum, confirming that water sublimation is occurring, even if it's not the dominant process. The water comes from somewhere on or near the nucleus, adding its contribution to the overall coma. The presence of water means we should see the familiar water-related chemistry that drives so much of normal cometary behavior. Hydroxyl radicals, hydrogen emissions, oxygen lines. We do see those things. They're there in the data. They're just quieter than expected, overshadowed by the carbon dioxide dominance. Polarimetry adds another dimension to the mystery. When light scatters off particles in the coma, it acquires polarization that depends on the particle's size, shape, and refractive properties. Observations of 3I Atlas showed negative polarization, more extreme than typical comets or asteroids. This suggests the dust grains are either unusually large, unusually fluffy with low density, or made from materials with different optical properties than solar system dust. The negative polarization could indicate that the dust formed in a different environment, under different conditions than the dust we're familiar with. If 3I Atlas originated in a molecular cloud with different chemistry than the one that birthed our solar system, its building blocks might have fundamentally different characteristics. Different carbon to oxygen ratios, different grain sizes, different ice mantles coating the dust. NuSTAR's search for hard X-ray emission came up empty, which is both reassuring and disappointing. Reassuring because it rules out exotic high-energy processes like particle acceleration or radioactive decay. Disappointing because a positive detection might have pointed toward new physics that could explain the soft X-ray anomaly. The null result confirms we're dealing with standard charge exchange physics, just operating under conditions or geometries we don't fully understand. Phase angle matters more than casual observers realize. The angle between the Sun, the comet, and Earth determines which parts of the coma we see illuminated, and how foreshortening affects our perception of structure. A tail pointing nearly directly away from Earth appears compressed. A coma viewed from certain angles can hide asymmetries. 3I Atlas's phase angle during the XMM Newton observations might have conspired to produce the observed compactness. Might have. Probably didn't. But might have. The comparison with 2I/Borisov haunts these discussions. That earlier interstellar visitor behaved exactly like a solar system comet. It had proper tails. It showed normal outgassing patterns. Its chemistry, while slightly unusual in some respects, fell within the range of variation observed among solar system comets. 2I/Borisov suggested that interstellar comets are basically the same as our comets, just formed around different stars. 3I Atlas is destroying that comfortable assumption. If interstellar objects can vary this wildly, if they can present chemistries and behaviors that depart significantly from solar system norms, then every interstellar visitor needs to be treated as potentially novel. We can't assume they'll follow patterns we've established through centuries of studying our own system's objects. The spectrum of cometary behavior might be much wider than we thought. Solar system comets might represent one narrow band of possibilities, shaped by the specific conditions in our protoplanetary disk. Other stellar systems, formed from molecular clouds with different compositions, might produce comets with radically different volatile inventories, dust properties, and activity patterns. 3I Atlas could be our first real glimpse of that diversity. Or it could be an outlier, a statistical fluke, an object whose properties happen to fall outside the norm but don't represent a new category. With a sample size of 3 interstellar objects, we can't distinguish between systematic differences and random variation. The frustration in the community is palpable. We have excellent data. We have sophisticated models. We have decades of experience interpreting cometary observations. And yet, this one object refuses to fit neatly into our framework. It sits at the boundary between known and unknown, familiar and alien, constantly suggesting that we're missing something fundamental about how these objects work. What if comets are more diverse than we ever imagined? What if the solar system's inventory represents a biased sample, shaped by local conditions that don't apply across the galaxy? What if interstellar space itself transforms these objects, altering their surfaces and compositions in ways we're only beginning to appreciate? These questions don't have answers. Not yet. But they're the right questions to ask. And asking them is the first step toward understanding what 3I Atlas is trying to teach us. The internet has opinions about 3I Atlas, and not all of them involve peer review. Online astronomy communities have been tracking this object with the intensity usually reserved for major spacecraft missions or potential Earth-impacting asteroids. Discussion forums overflow with amateur observations, spectral analyses, and increasingly heated debates about what the data actually means. Some of these discussions are scientifically sound. Others venture into territory that makes professional astronomers wince. One recurring claim suggests that 3I Atlas's orbital motion shows anomalies inconsistent with pure gravitational physics. Specifically, some analysts argue that the object's trajectory deviates from predictions in ways that can't be explained by standard cometary outgassing forces. These non-gravitational accelerations, they claim, exceed what carbon dioxide sublimation should produce, hinting at either unusual internal activity or, in more speculative threads, something more exotic. The professional response to these claims has been measured skepticism. Non-gravitational forces are well documented in cometary physics. When gas sublimates from a rotating nucleus, it creates thrust, like a very slow rocket engine. This thrust alters the orbit in predictable ways. The magnitude depends on the rotation rate, the distribution of active regions, and the gas production rate. For most comets, these effects are small but measurable. For 3I Atlas, calculating non-gravitational forces is complicated by uncertainty about the nucleus's rotation, shape, and activity distribution. Without detailed knowledge of these parameters, you can't predict exactly how outgassing should affect the orbit. Claims of anomalous acceleration might simply reflect incomplete modeling rather than genuine deviations from physics. But the claims persist, fueled by the fact that precise orbital tracking requires time and careful analysis, neither of which stops internet speculation. Another controversy involves reports of the tail disappearing and reappearing. Multiple observers claim to see the dust tail fade to invisibility over the course of days, only to re-emerge later. Mainstream interpretation attributes this to geometry. As the comet rotates and moves through space, our viewing angle changes, making tails appear and disappear based on foreshortening and illumination conditions. This explanation is almost certainly correct. Tails aren't solid structures. They're diffuse collections of particles and gas that scatter light based on geometry. Change the geometry, change the visibility. We've seen this behavior countless times with other comets. Yet some observers insist the changes are too rapid or too dramatic to blame on geometry alone, suggesting instead that the nucleus is experiencing episodic outbursts, sudden increases in activity that temporarily enhance tail brightness before subsiding. Outbursts are real phenomena. Comets do experience sudden activity surges. But distinguishing outbursts from geometric effects requires careful analysis of brightness changes corrected for viewing conditions. The discussions about antitails add another layer of intrigue. An antitail is an optical illusion where dust particles lagging behind the comet in its orbit appear to point toward the sun rather than away from it. It's a perspective effect, well understood, and commonly observed. 3I Atlas has shown anti-tail features in some images, prompting extensive amateur analysis. Professional astronomers acknowledge these features as normal anti-tail phenomena. Some community members interpret them as evidence of unusual dust dynamics or jet orientations, reading significance into structures that have mundane explanations. Perhaps the most persistent controversy involves claims of information suppression. Online threads occasionally suggest that certain observations are being withheld, that data exists showing even stranger properties of 3I Atlas, but hasn't been released to the public. These claims usually cite delays between observations and data publication, or restrictions on access to certain telescopes, as evidence of deliberate concealment. The reality is far more boring. Astronomical observations go through systematic processing, calibration, and analysis before public release. Telescope time is competitive. Researchers who win observation slots receive proprietary periods during which they have exclusive access to the data, allowing them to analyze and publish results before everyone else gets a look. This isn't conspiracy. It's standard practice designed to protect the investment of time and effort that goes into requesting observations and securing telescope access. Data release timelines are published openly. Everyone knows when proprietary periods end. The suggestion that mundane operational procedures represent information embargoes reflects misunderstanding more than malice. But misunderstanding is powerful. Once suspicion takes root, every delay or restricted dataset becomes evidence of cover-up. The fact that professional astronomers are being cautious in their interpretations, waiting for peer review and additional observations before making strong claims, gets reinterpreted as evasiveness or hiding something. The tension between professional caution and public curiosity creates fertile ground for speculation. People want answers. They want to know what 3I Atlas is, whether it's natural, whether it represents something unprecedented. Scientists want those answers too, but they're bound by methodology that requires patience and rigor. Alternative physics discussions occasionally surface, usually framed as thought experiments rather than serious proposals. What if 3I Atlas has a weak magnetic field that channels solar wind in unexpected ways? What if surface cohesion forces differ from solar system materials, affecting how dust separates from the nucleus? What if rotation patterns create outgassing geometries we haven't encountered before? These aren't crazy ideas. They're creative hypotheses that explore parameter space beyond our current experience. Some of them might even be correct. But testing them requires data we don't have yet. Detailed surface imaging, magnetic field measurements, rotation period determination, spectroscopic mapping of activity distribution. The community is doing its best to separate signal from noise, to identify which anomalies are real and which are artifacts of observation or analysis. This process is messy. It involves disagreement, revision, and occasionally admitting that earlier interpretations were wrong. Science at the frontier always looks chaotic from outside. What's frustrating is that 3I Atlas doesn't need exotic physics to be fascinating. An interstellar comet with extreme carbon dioxide dominance and unusual X-ray properties is already extraordinary. We don't need to invoke alien technology or undiscovered forces to make this object worthy of attention. But the human mind craves certainty and significance. When faced with ambiguity, we construct narratives that resolve the tension, even if those narratives require abandoning Occam's razor. 3I Atlas has become a Rorschach test, revealing as much about our need for cosmic meaning as it does about the object itself. Let's be clear about what we're doing here. We're entering speculation territory, the zone where data ends and imagination begins. Everything that follows is hypothesis, thought experiment, and what-if scenario. Some ideas are grounded in physics, others are purely exploratory. None are confirmed, but speculation has value. It opens mental space for possibilities we might otherwise dismiss. It helps us ask better questions, even if the answers aren't what we expected. So let's speculate responsibly about what 3I Atlas might be. Hypothesis A. 3I Atlas is an unusually dense solid body with an extremely thin, chemically atypical coma. Most comets have porous, fluffy nuclei with densities below 1 gram per cubic centimeter, basically dirty snowballs with lots of empty space. What if 3I Atlas is different? What if it's a denser object, closer to solid rock or ice, with lower porosity and different mechanical properties? A denser nucleus would sublime more slowly for a given amount of solar heating, because thermal energy takes longer to penetrate and warm the interior. This could produce a thin coma with unusual density profiles. The carbon dioxide dominance might reflect surface layers that preferentially lost water during billions of years of cosmic ray bombardment in interstellar space, leaving carbon dioxide-rich residues. The compact X-ray emission would then result from the limited extent of the coma. Only the immediate vicinity of the nucleus has enough gas density for charge exchange. Beyond a certain radius, the coma is too tenuous to produce detectable X-rays. This hypothesis is testable. It makes predictions about the nucleus size, rotation period, and thermal properties that can be checked against observations. If the nucleus rotates slowly, if thermal modeling shows unusually high thermal inertia, if the coma density falls off more steeply than expected, all of these would support the dense body interpretation. We could even estimate the nucleus's bulk density by measuring how much sunlight it reflects versus how much gas it produces, comparing energy input to sublimation output. The dense body hypothesis also explains why optical observations show typical comets, features while X-rays don't. A thin but real coma would scatter sunlight efficiently, creating visible tails and fuzzy appearances in photographs. That same thin coma, spread across a large volume, might be too diffuse everywhere except near the nucleus to generate strong X-ray emission. The physics stays consistent. The object just operates at different density regimes than we're accustomed to seeing. Hypothesis B: the coma chemistry is so unusual that it fundamentally alters charge exchange efficiency. Not all atoms participate equally in X-ray generation. Oxygen and carbon are good targets, but the molecular environment matters. If the carbon dioxide molecules in 3I Atlas's coma have different energy states or dissociation patterns than what we see in solar system comets, the charge exchange cross-sections might be suppressed. Additionally, if trace elements in the coma catalyze different chemical pathways, the distribution of neutral atoms available for charge exchange could be radically different. The X-ray morphology depends not just on total gas production, but on the spatial distribution of specific atomic species. This hypothesis requires detailed chemical modeling and additional spectroscopy to test. We'd need to map the spatial distribution of different molecular species in the coma, measuring how carbon dioxide, carbon monoxide, water, and other volatiles vary with distance from the nucleus. We'd need laboratory measurements of charge exchange cross-sections for unusual molecular configurations. We'd need to understand whether carbon dioxide dissociation in solar ultraviolet light produces atomic distributions fundamentally different from water dissociation. The chemistry hypothesis is attractive because it doesn't require the object to be physically strange, just compositionally unusual. Carbon dioxide-rich comets might be common in certain stellar environments. If the molecular cloud that birthed 3I Atlas's parent star had elevated carbon to oxygen ratios, the resulting planetary system would naturally produce comets with carbon dioxide dominance. We're simply seeing the consequences of different initial conditions playing out in observable ways. Consider what happens when carbon dioxide molecules absorb sunlight. They can dissociate into carbon monoxide plus atomic oxygen, or into atomic carbon plus molecular oxygen, or undergo more complex fragmentations. Each pathway produces different atoms with different velocities and spatial distributions. If 3I Atlas's carbon dioxide follows unusual dissociation pathways, perhaps catalyzed by trace contaminants we haven't detected yet, the resulting atomic populations might be concentrated near the nucleus or expelled at velocities that reduce charge exchange efficiency. Hypothesis C: interstellar space leaves marks. 3I Atlas spent millions or billions of years traveling through the galaxy, exposed to cosmic rays, interstellar radiation, and possibly encounters with molecular clouds. These exposures might have altered the surface chemistry, creating radiation-damaged layers with properties unlike fresh solar system materials. Cosmic ray bombardment can break chemical bonds, rearrange molecular structures, and implant new atoms into surface ices. Over geological timescales, these processes could create a surface mantle with unusual composition and physical properties. When this altered material sublimates near the sun, it might produce a coma with unexpected characteristics. This hypothesis is harder to test directly, but makes predictions about surface spectra and the evolution of activity as deeper, less processed layers become exposed. If the surface is radiation damaged, we might see spectral signatures of unusual molecules created by radiation chemistry. Complex organics, carbonyls, peroxides, molecules that don't normally exist in comet ices, but form when high-energy particles rearrange chemical structures. As sublimation removes the damaged surface layers, exposing fresher material underneath, the coma composition might change over time. Early observations would show radiation products. Later observations, as pristine interior ice becomes exposed, might reveal more typical compositions. Tracking these changes would provide evidence for or against the radiation mantle hypothesis. The interstellar journey matters more than we usually acknowledge. Solar system comets spend most of their existence in the Oort cloud or Kuiper belt, relatively protected from galactic cosmic rays by the sun's magnetic field and the heliosphere. Interstellar comets have no such protection. They swim through the full intensity of galactic radiation for millions of years. That exposure must leave marks. The question is whether those marks affect observable properties. Now, we enter more speculative territory, clearly flagged as such. Fringe hypothesis. Alpha. 3I Atlas possesses a weak intrinsic magnetic field, or generates one through some internal process. If the nucleus contains magnetic materials, or hosts plasma currents, it might create a magnetic bubble that deflects solar wind before it can interact with the neutral coma. This would suppress X-ray generation while allowing optical and UV signatures to proceed normally. There's no evidence for cometary magnetic fields of the required strength. The idea is physically possible, but unsupported by data. Cometary nuclei are generally assumed to be non-magnetic because they're composed of ices and rocky materials that don't generate strong fields. But what if 3I Atlas contains iron-rich minerals magnetized during its formation? What if internal convection or plasma circulation somehow generates weak fields? A magnetic barrier would be invisible in most wavelengths, but would dramatically affect solar wind interaction. Charged particles would be deflected around the obstacle, creating a magnetic cavity within which neutral gas could exist without experiencing charge. Exchange. The X-ray emission would be confined to the boundaries of this cavity, potentially creating the compact morphology we observe. This is speculative physics. It requires conditions we have no evidence for, but it illustrates how unfamiliar internal structures could produce unexpected external behaviors. Fringe hypothesis. Beta. An unknown physics mechanism alters X-ray generation in extreme chemical environments. Perhaps carbon dioxide-dominated comas create electric field configurations that inhibit charge exchange. Perhaps there are density thresholds below which quantum effects modify collision dynamics. This is pure speculation, invoking new physics without justification. It's the kind of idea you entertain when standard physics fails comprehensively, and we're not there yet. But consider, charge exchange is a quantum mechanical process. The cross-sections depend on orbital overlaps, energy levels, and particle velocities. In extreme environments with unusual molecular species at unusual densities, could there be regime changes in how these processes operate? Probably not. Almost certainly not. But the history of physics includes examples where familiar processes behave differently under extreme conditions. We don't have X-ray observations of carbon dioxide-dominated comets because solar system comets aren't carbon dioxide-dominated. 3I Atlas is our first real test case. Perhaps it's teaching us that our models, calibrated on water-rich objects, miss important details when applied to radically different chemistries. The value of these hypotheses isn't that they're likely to be correct. Most will be wrong. Their value lies in expanding the solution space, encouraging researchers to consider possibilities beyond the first obvious explanations. Sometimes the truth hides in parameter space we didn't think to explore, because our assumptions made it seem irrelevant. Think of 3I Atlas as a chunk of exotic ice behaving unpredictably in heat. We understand ice. We understand heat. But when the ice comes from an alien freezer, when its molecular structure reflects formation conditions we've never studied, our intuitions might fail. The ice still follows physics, but the details matter, and we don't know all the details yet. Responsible speculation requires acknowledging uncertainty. These ideas are tools for thinking, not claims about reality. The scientific process will sort them out. Observations will continue. Models will be refined. Some hypotheses will survive contact with data. Others will collapse under scrutiny. What matters is maintaining intellectual honesty about what we know versus what we're guessing. 3i Atlas is teaching us that the boundary between those categories is less clear than we'd like. We know it's an interstellar object. We know it shows cometary activity in some wavelengths. We know its X-ray properties are unusual. Beyond that, we're constructing narratives to connect observations into coherent stories, but those narratives remain provisional until confirmed by additional evidence. The discomfort is productive. It drives better observations, more careful analysis, more creative modeling. 3i Atlas is making us better scientists by refusing to fit neatly into our categories. Whether it represents genuine novelty or simply an extreme case within known physics, the effort to understand it advances our knowledge. And that's the point of exploration. Not to confirm what we already believe, but to discover where our beliefs need revision. 3i Atlas is a teacher disguised as a mystery, and we're fortunate to have this opportunity to learn from it before it disappears back into the darkness between stars. 3i Atlas isn't alone in challenging our assumptions this year. The universe has been particularly generous with surprises lately, each one chipping away at the comfortable frameworks we use to make sense of cosmic diversity. Earlier in 2025, the Subaru telescope released results from a survey of exoplanet systems that found massive planets and brown dwarfs in orbital configurations that shouldn't exist according to standard formation models. These objects sit at the boundary between planet and star, with masses up to 80 times Jupiter's, orbiting their host stars at distances where gas giant formation is theoretically impossible. The discovery forces reconsideration of how planets form and migrate. Maybe disk instabilities can create massive objects directly from gas collapse without requiring core accretion. Maybe planetary migration is even more common and dramatic than current models assume. Maybe the categories we've created, planet versus brown dwarf versus star, represent artificial boundaries imposed on a continuous spectrum of possibilities. The theme is familiar. Nature is more diverse than our theories anticipated. The James Webb Space Telescope continues to be an engine of discomfort for astrophysicists. Its infrared eyes are revealing atmospheric compositions in exoplanets that contradict predictions based on solar system chemistry. Planets with carbon to oxygen ratios inverted from Earth's. Worlds with atmospheric hazes made from molecules we didn't expect. Systems where water is rare and methane dominates in pressure-temperature regimes where Earth-like chemistry should prevail. Each discovery expands the parameter space we need to consider when thinking about planet formation, evolution, and habitability. The solar system, once again, appears to be a potentially biased sample of a much larger population of possibilities. Then there's the pre-solar stardust found in samples returned from asteroid Bennu. Tiny grains, smaller than sand particles, older than the solar system itself, that survived the formation of our star and planets to end up embedded in an asteroid surface. These grains came from other stars, from supernovae and dying giant stars, and they carry chemical signatures of nucleosynthesis processes that occurred billions of years before Earth existed. The discovery is humbling. It means that pieces of other stellar systems, literal fragments of stars that died long ago, are mixed into the raw materials that built our world. Interstellar material doesn't just visit our solar system as comets and asteroids from outside. It's woven into the very fabric of the planets and moons we call home. This connects directly back to 3i Atlas. If pre-solar grains survived incorporation into our solar system's building materials, if interstellar chemistry influenced the composition of our own comets and asteroids, then the distinction between solar system objects and interstellar objects might be less absolute than we think. We're all made from stardust. Some of that dust is local. Some traveled from far away. The boundaries blur. 3I Atlas fits into this broader narrative of cosmic diversity and interconnection. It's a visitor from interstellar space, yes, but it's also a sample of the same processes that built other planetary systems. By studying it, we're not just examining a curiosity. We're gathering data on how comets form and evolve in environments different from our own, learning about the range of compositions and properties that nature permits. The carbon dioxide dominance in 3I Atlas might tell us something about the molecular cloud from which it formed. Different regions of the galaxy have different chemical abundances. Stars forming in carbon-rich environments might produce planetary systems with unusual volatile inventories. 3I Atlas could be a messenger from such an environment, carrying information about chemistry occurring light years away. The unusual X-ray properties might reveal something about how long the object spent in interstellar space. Cosmic ray exposure, bombardment by energetic particles, slow chemical evolution over millions of years, all of these processes could leave signatures in the object's composition and physical structure. By decoding those signatures, we learn about conditions between the stars, about the interstellar medium that connects stellar systems into a galactic ecosystem. Every discovery this year reinforces the same lesson. The universe is larger and stranger than our theories accommodate. We build models based on local observations, then get surprised when distant or unusual objects don't conform. The surprise is a gift. It tells us where our models need expansion, where our assumptions need revision, where new physics or chemistry or dynamics await discovery. 3I Atlas is one such gift. It arrived unannounced, behaved unexpectedly, and forced us to question what we thought we knew about comets. Whether it represents a genuinely new category of object or simply an extreme case within existing categories doesn't diminish its value as a teacher. The broader cosmic context reminds us that Earth, the solar system, even our galaxy, are embedded in a universe that operates on scales and principles we're still learning to comprehend. Interstellar objects are threads connecting our isolated system to the galactic tapestry. Each one brings news from distant shores, hints about what's possible, evidence of processes we can't witness directly. We're living through a golden age of discovery. Instruments like Webb, missions like Bennu sample return, observations like those of 3I Atlas, they're collectively rewriting our understanding of cosmic architecture. The textbooks published today will be outdated in a decade. The models we use to explain planetary systems, comet formation, and stellar evolution are works in progress, constantly refined, and occasionally revolutionized. The philosophical dimension matters too. These discoveries affect how we see ourselves and our place in the cosmos. When we find presolar grains in asteroid samples, we're holding matter that existed before the Sun, before Earth, before anything we call familiar. When we detect interstellar comets with chemistries unlike our own, we're reminded that our system is one example among billions, shaped by local conditions that don't universally apply. Humility seems like the appropriate response. Not the humility of defeat, but the humility of wonder. We're clever enough to detect these objects, sophisticated enough to measure their properties, curious enough to ask what they mean. But we're also small, new to this enterprise of understanding the universe, working with incomplete information and provisional theories. 3I Atlas will leave our solar system and return to the interstellar void. It will continue its journey for millions of years, perhaps encountering other stellar systems, perhaps being perturbed into new orbits, perhaps eventually ending up as part of some distant world. We had a brief window to study it, a few months when our paths crossed and our instruments could reach it. What we learned and what we failed to learn will inform how we approach the next interstellar visitor. Because there will be a next one, and another after that. The galaxy is full of these objects, wandering between stars, carrying information about cosmic diversity. Each visit is an opportunity. Each observation is a data point. Each mystery is an invitation to think harder, build better instruments, ask smarter questions. The universe keeps surprising us. That's not a bug. That's the whole point. Somewhere out there, right now, another interstellar object is on a trajectory that will bring it through our solar system years or decades from now. It might behave like 2I/Borisov, confirming that some things are universal. It might behave like 3I Atlas, adding new puzzles to unsolved lists. It might behave like nothing we've seen before, forcing us to expand our categories yet again. We'll be watching, we'll be ready, and we'll be grateful for whatever it teaches us about the strange, beautiful, endlessly complex cosmos we inhabit.